After I will stop. Okay, this is my presentation. This is like a hands-on introduction to Gsmh. So we're gonna present again what Gsmh is in short, and we're gonna try to make it work on the 2D example in the 3 ways that you could use Gsmh on your laptop. So I borrowed this license from Bruno Bleu's presentation on Python a while back. So thank you. Okay, so what is Gsmh? So as Jean-François said, it's an open source software that's has 3 well actually 4 main modules. So the first one is that it's a basic Cad modeler. When I say basic, I don't mean it in a mean way. I just mean it wasn't meant to be a Cad modeler like Katia or SolidWorks, but you can do basic geometry and basic CAD models quite easily, and or repetitive geometries. So it's very handy when you just want to make a square, a rectangle, a block, or even more complex geometries, but maybe not a full block, a full motor block, for example. And it's mostly a mesh generator in 1D, 2D, and 3D, mostly with triangles and tetrahedra. And it has also many tools to perform quad meshing and hex meshing. It also features, it's also an interface to external solvers. So external, for example, finite element or finite volume solvers through the OneLab interface. I won't be talking about this today. I will mostly be talking about the geometry modeling, the mesh generation. I have one slide on visualizations. You can use Gsmh as your visualization software, and it has a few post-treatment tools that are very handy too. And it's, as I said, an open source software that's under active development, which you can access on the website or on the Git repository. And how do you use it? So basically, you have 3 ways to use Gsmh. The first one is it's through the GUI, so the graphical user interface, which is called the interactive mode in the documentation. You can use it in command line through your terminal, which is the non-interactive mode. And you can program using Gsmh, that is using the API, the application programming interface, that comes in 4 flavors and in 4 languages, C, C++, Python, and Julia. So in this presentation, it will be essentially the first steps with Gsmh, and we're going to take a look at 2D geometry and mesh it with and produce an unstructured mesh of triangles of this geometry. So it's meant to be an easy tutorial, and it's a bit in line with what I do. So unfortunately, there's no 3D fancy geometries, but hopefully you'll find something useful from the presentation. So I'm going to present you how to mesh this 2D geometry through create the geometry through the user interface, and the whole process in command line and through the API. So I'm going to put the emphasis on what I think is it's easier to use Gsmh through command line or the API, because there's a lot more tool and you have much more control on your model than through the GUI. But that's my opinion, and if you're comfortable with the graphical interface, go for it. And then I have one slide to show you how you can visualize data with Gsmh, and I will conclude with a short example of mesh adaptation through the C++ API. So let's start. Let's consider this geometry. So it's essentially a rectangle with a cylinder in the middle, and you can use this geometry, for example, to simulate the flow, the steady flow of Newtonian fluid around a cylinder. And essentially, the only important information on the slide is the shape of the geometry and the fact that we're going to be using the same boundary condition on gamma 2, that is on the top and bottom. And why is that? Because I just wanted to motivate the use of what is called physical entities, which I will explain in a minute. Essentially, it's a geometry, and we are going to give names to the boundaries like this. And the two top and bottom boundaries will have the same name and will actually be one and the same entity, just because there's one boundary condition that is the same defined on those two entities. So in a nutshell, what we're going to do is we are going to create what is called the geometric entities, which are essentially the building blocks of the geometry. So there are points, curves, surfaces, and volumes if you're handling the 3D case. Here it will just be point, curves, and surfaces in one surface. And then we shall define what is called in Gsmh the physical entities or the physical groups, which are essentially named groups of geometrical entities. So I will explain in a minute why it's useful to define physical entities. But as you can guess, for example, here if you have one boundary condition defined on more than one curve, well, it's pretty handy to define a physical group that is a group of those curves. And then to actually to help Gsmh generate the mesh, we're going to specify the size of the elements, and that will actually generate the mesh. So creating the geometrical entities. Oh yeah, just before, to create the geometry in geometry modeling, usually you have two ways of representing the geometry, which is called, the first one is called the boundary representation, or the BREP. And essentially, 3D object is a volume that is bounded by surfaces. Surfaces are each bounded by a certain number of curves, and each curve is bounded by 2 points. And if you describe the points, then the curves, the surfaces, then you can describe the whole geometry by splitting it and describing it in a bottom-up fashion. The other way is what is called the constructive solid geometry. And typically you describe, for example, this geometry by a series of Boolean operations from volumes. So instead of saying the boundary of this volume is going to be a bunch of circles and the rest is pretty difficult to describe, I'll just say it's the intersection of a cube and a sphere, and I will subtract from this the intersection of those three cylinders. So these are the two main ways of describing a geometry. And in Gsmh, this is the BREP that is used. You can also do CSG, but how it's done in the tutorials and how it's done instinctively, well, not instinctively, but how it's the primary way of describing the geometries are through a BREP. So that's what we're going to do here. We're going to create points, add lines, surfaces, and then volume. So first part is going to create the geometry through the user interface. So when you open Gsmh, you have something like this without the window and the square. We have this menu you can unroll, in which features essentially the geometry module, the mesh module, and the solver module that are hidden here. So the first thing we're going to do to generate, just a reminder, we want to generate this geometry. We're going to add the 4 points, add a circle, connect the points with curves, and add the surface. So first thing we're going to do is to set the Cad kernel to the Open Cascade kernel. So what this means is that Gsmh comes with 2 Cad kernel. It's a Cad kernel it's an implementation of Cad functions and Cad figures, and there are 2 in Gsmh. There is the built-in native Cad kernel, which makes basic geometries, and then there's the Open Cascade, which is used for a bit more fancy geometries, such like ellipses, circles, etc., etc. So in our case, since we're going to use a circle that is an Open Cascade function, to know which is which, it's all said in the documentation. Since we're going to use a circle, we're going to set the Open Cascade Cad kernel. And then we're going to add the 4 corners. So you can, when you open Gsmh, you're going to unroll the geometry and then the elementary entities, which are the building blocks, and click on point. Well, first click on Open Cascade, then click on point. You're going to add the 0, 0, and then at the point, etc., for all the corners. So this is the size of my rectangle. And then you're going to add the line simply by clicking on line and clicking on the beginning and ending point of the line. As you can see, there's a default prescribed mesh size at each point you add, which at least in my version is 1. You can leave it at 1 for now if you want to try, and we're going to modify it afterwards. So once we added the line, we can add the circle. You specify the center, the radius, and then you add the circle. And then we're going to add the plane surface, which is going to be bounded by the exterior boundary, which are our 4 lines. And then you can specify any number of holes in the plane surface. So what you're going to do essentially in Gsmh, you're going to click on plane surface and select any point on the boundary. It's going to select it as a hole, which is called a curve loop, which you're going to see in a minute. And then it asks you if you want to add any hole in the representation. And then you can click on the circle to define the surface as the lines minus the circle. Yeah. So it will essentially, I mean, our domain, our computational domain will be the inside domain. So at this point, we could already generate a mesh. So what I mean is, as I said before, to generate the mesh, you need to have a size instruction at each point of the geometry so that the mesh algorithm knows what size you'd like to have for your triangles at each point in the domain. And it's typically called a size field or a size map, une carte de taille en français. And it's a function typically written h of x that just returns the ideal mesh size everywhere in the geometry. And by default, when you specified 1 as the mesh size at the point, well, since there is no other mesh size available, Gsmh is going to interpolate first the 1 value here from the point to the curves, and then from the curves to the domain, okay, to the inside domain, so that the mesh size in the domain is given only by your 4 points. And I think maybe there's a default size from on the circle, because as you can see, it's around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 elements on my from 0, 0 to 10, 0 line, so that checks out. It's a bit smaller here, probably because there's a default mesh size that has been assigned by OpenCascade when you call the circle function. So Jean-François may confirm that afterwards. And yeah, so there's a default size field that is built by Gsmh by interpolation of your nodal size value. And then if you're in the user interface, so in this window, you can scroll down, go on the mesh menu that's hidden here, and you can just click on 2D or simply press 2 on your keyboard, and it will generate a mesh of your surface. If you forgot to use the step 0 and you did not click on Open Cascade, it will probably generate this mesh because it's an error. It's not valid. It's just because essentially you created the first points in the built-in kernel, and then you created the circle in the Open Cascade kernel, and they all have different, which are called tags, so basically identification numbers, and they don't communicate. So it will try to do the best as it can with different identification, each starting at 1, and it's a mess, and it's going to mesh the surface you don't want to mesh. It's essentially going to create a surface that is bounded by this loop of lines instead of this one. So this is not what you want to do, of course. Yeah. So for this is as far as I will go on the GUI, simply because I don't think it's very handy to work with the GUI to specify size fields. So I'm going to do the rest either in command line or through the GAPI. But if you want to absolutely work with the GUI, we can talk a bit. We can talk about it afterwards. So the next step is going to, I'm going to redo the same step, so creation of the geometry in command line and with the API. But first of all, I just want to talk a little bit about the what I usually call the Geo language, which is essentially Gmsh built-in language. So Gmsh comes with the it comes with its own programming language, which is called the, I think, Gmsh language. I'm not sure there's a proper name for it. I call it Geo language, but whatever. And it supports two types of variables. So essentially real, which are double, and the string types of character. And in the following, I give some example of function calls. Whenever I don't specify the type, so instead of putting real tag here, the real is implied. So every time there's only one parameter, it's because I mean it's a real that is sous-entendu. Okay, and whenever it's a string or a list of reals, so expressions, I'm going to specify it like this: expression list and then the name. There's also a very handy rule that comes in when you manipulate the Geo language. All the variables that are inside parentheses typically refer to a new entity, or they will likely create the new entity, the new variable that's in parentheses. And when you use braces, you will refer to an existing variable. So that, for example, when you want to create a point with the Gmsh language, you're going to call the function point. This is, I forget how to say that, but sous-entendu that the type of the tag is expression, that is a double. So it's essentially point of double tag, and it will create a new tag, so a new identification number for your point. So you will typically call it with point 1 to start. Give the coordinates, which are all expression, that is all real or double numbers, and you will specify a characteristic length. Well, characteristic length is the old calling, but now it's mesh size. But you will specify the coordinate and the mesh size you want to assign to this point. Then if you want to create lines, you're going to call the function line. It will create a new tag it will create a new tag that will be proper to the dimension of the entity you're creating, so that you can call line 1 because points and lines are different dimensions, so they can have the same identification number. But if you create 4 lines, you have to use tag 1, 2, 3, 4, or 1, 2, 8, 20, whatever, but you cannot repeat the tag within 2 same dimension entities. And typically you will create a line by calling the tag of the first point and the tag of the second point of the line. And it works in a similar fashion for Bezier curves, B-splines, circles. So here, for example, for a B-spline, you're going to enter a list of control points, so a list of tags instead of just 2 tags. And for a circle that we're going to use right afterwards, we're going to enter the coordinates of the center, the radius, the begin and the end angle, so 0 to pi for a full circle. Once this is done, and what was done implicitly by the GUI, the user interface, is that it's going to create what is called a curve loop, which is essentially an oriented loop of curves, and you're just going to give it a new tag. And you're going to say, for example, I want my lines 1 to 4 to be a part of a curve loop. And because the curve loops are going to be used to define the surfaces. So, for example, the plane surface from the previous example, it can be just created by saying, I want to create a new plane surface with my tag. For example, plane surface 1. I can use 1 again because it's 2D now. And I'm going to give the tag, it's a long name, but it's just a tag, for example, 1 of the boundary curve loop. So for example, well, I'll show you these are all just function calls, but I give you the proper example in just a second. You're going to give first the boundary curve loop, and then you're going to give a list of holes you want to add to the geometry, but the list can be the list can be empty. So you can call plane surface with just one parameter here, which is the boundary, and it's a full surface without holes. So you have other functions to call to create a surface that's not necessarily plane, a rectangle, a disk, etc. And then we won't be using it in this presentation, but you can add in a similar fashion a surface loop instead of a curve loop. And a surface loop is going to be a list of surfaces that are used to define volumes. Okay? And you have also built-in functions to create specific volumes such as a sphere, cylinders, etc., etc. So I'll come back to this slide in a second. I'm just going to show how we use this. So we're going to create the geometry, and this is inspired by tutorials from the Gsmh documentation. So I put the relevant numbers here in the corner. So if you want to refer later to the tutorial, you have the number. So in our case, we're going to write a, I don't know if you can see it. Yeah, that's what I call foo.geo. .geo is the Gsmh script format. And we're going to write this in the foo.geo. We're going to set the kernel factory to open cascade, just like we did in the GUI. We're going to define a few variables. So my corners, the coordinates of my corners of the rectangle, and then the center of my cylinder, and then its radius. We're going to set the mesh size. So I'm going to use 0.2 0.2 at all points. And then I'm going to add the 4 points. So 0.1 is a new tag. 0.1 is going to be if min, y min with the mesh size, 0.2, 0.3, 0.4. I'm going to create 4 lines like I did in the GUI by clicking on the points. The orientation is important because a line can be reversed. So if you want to go from 4 to 1, you have to write 4, 1, another 1, 4. And we're going to add a circle. So lines and circle are different functions, but they both create curves, so 1D entities. So that means I cannot, I have to use a new tag for the circle, as you might have guessed. And it's, this is the radius, the center radius from 0 to 2 points. And then we're going to, I'll come back to that in a second, but we're going to define a curve loop with the boundary, and then another curve loop with the circle, because we need curve loops to define the surface. And then we're going to define a surface simply by the surface that is bounded by the first, and with a number of holes equal to the supplemental curve loops I give, that is 1, and it's going to be the circle. This means that, and that's why even you have more control with the GeoScript than within the interface. But even in the GeoScript, there are a bit secret stuff that are happening. For example, when I use circle 5, the Open Cascade kernel added a point to create the circle. So they actually added a point entity that I'm not aware of, and its number is 5. So you can try, if you want to try to add a 0.5 after you use circle, it's going to say, hey, the tag number 5 is already used, even though you didn't create it yourself. So there's a bit of hidden stuff happening in the background. So since you're intelligent people, you figured out, oh, okay, 0.5 was created by circle, and you can assign a mesh size to the 0.5, because otherwise you're going to say, hey, I didn't get a chance to give a mesh size to the circle. You can by addressing its tag, but you have to maybe reverse engineer a bit to get the tag, or maybe there's another way that GF is going to explain. So let's say I want to modify the size of the circle to give it 0.01. And this is not used in this example, but if I wanted to indeed add a new point, I cannot use 5 because 5 was taken, but I can use p5, the variable, which is going to be the function new point. New point is going to return me the next available tag for points. So I can move on with my life and create point p5, and it's going to be, for example, in 1, 1 with the same mesh size. Okay, and then I'll come back to the physical in just a second. Actually, I'm gonna present this slide first because this is the explanation of the physical that I'm skipping from the beginning. So essentially what I told you in the beginning, I think most of you understand, but a geometric entity is essentially a construction block. So the points, the lines, the surfaces we've been building. And so here in an example, we have 5 curves and 1 surface. And then we can combine them as we wish, as long as they have the same dimension together, to make relevant groups. For example, we can have the domain that's an association of, I mean, the computational domain can be an association of multiple domains. We can group, for example, all the curves on the boundary because we want to impose a 0 boundary condition on this. So we can, instead of manipulating 4 boundaries, we can just create 1 physical entity that will be used to assign boundary conditions. Or maybe because we have a geometry that's composed of many pieces, such as a plane's fuselage, a nozzle, etc. Or there are just different material properties, for example. I say here it's possible to save only physical entities, but it's actually more than that. If you have defined a physical entity, by default, it's only the physical entities that will be exported. So it's a bit harder than this. And why is it used? So, well, because of those reasons I just gave, but it's interesting because some, for example, finite element solvers, if you're using MFEM, they will only accept the Gsmh mesh format if you have created at least 1 physical entity. So you cannot use this geometry, export the mesh, and have it work with, for example, MFEM. Okay, so you, according to the solver, you might have to actually define at least 1 physical group. So I'll reverse a little bit, revert. How do you create those physical entities with the geofile? You're simply going to add the physical keyword in front. So for example, a physical point 1 is going to be now a list of all the points you want to create. So if you want to make a physical point that is for some reason going to be more than 1 point, you can, and you can give it a name. You can either give it a new number or a new name, and you can increment the geometrical entities that are part of this physical group. What I use a lot is the physical curves and surfaces. So it's exactly the same. You add the physical keyword. You either give a tag or a new name, and then you give a list of the curves you want to be part of the group, etc., etc. So in our script, it looks like this. For example, the physical. So this is the template I gave in the beginning. So they're all essentially each geometric entity is a separate physical group, except for the top and bottom, which are one and the same physical group, which is going to be both. Okay, and so I'm going to add a physical curve that is both, that has the name both, and it's made of the physical line. It's made of the geometrical line 1 and the line 3. And entrée is going to be the last one I created. Sortie cylinder is going to be 5 because it's related to this number, circle 5. And I can also add the physical surface for my surface. Okay. You might say, okay, why is this necessary? Just because by default, if I only added the physical curves, I will only export 1D elements at the end when I create the mesh. Since I want to export also the triangle elements, I had to add a physical domain for my surface. Okay, so I'm gonna put the script on GitHub right after the presentation, but if you wanna make sure we have the same thing as before, you can call Gsmh in command line just by writing Gsmh foo.geo, and it's going to create this geometry. So I have my 4 points and my circle, and you can see it created the point 5 that I was talking about. And you can display the physical entities, and you can check that this is entrée, this is in yellow is surface. Those two especially are one and the same, both physical curve number 2, physical curve number 2, and this is the outflow, the sortie. So it's all good. We talked about this. So now we've done the same as we did through the GUI. I mean, we added the physical entities. You can add the physical entities in the GUI as well. Okay, and it's quite easy. I didn't show you, but you can just press add physical entities and just click on the physical entities you want to add to a group and then enter a name. But when it comes very handy, it's here to specify the element size. So I told you before, you need a size field, so carte de taille, ou champ de taille in French. You need a size field to tell the algorithm what's going to be the size of the elements. And in Gsmh, the size is going to be determined by 4 factors. So the first one we talked already about is the LC, so the mesh size that you entered at the different points of the geometry, and it's going to be by default interpolated on the lines and on the surfaces. You can ask Gsmh to automatically compute a decent-ish size field from the curvature of the CAD. So essentially, you're going to give a number, and that's how many nodes you want per 2π perimeter. So if this is a very curved area and you want 50 points, there's going to be a lot of points in the curved area. I mean, in the curved boundary. The third one is the size field that we're going to define on the next slide. So Gsmh allows you to define fields, I mean, function of space, like f of xy, and you can use those fields to define the mesh size. And if you're using the API, you can make your own callback, so make your own function, and give it to Gsmh by setting a size callback that will be used as well. And then, of course, the most critical size is considered between those 4 contributions, and it's bounded by your custom min size and max size, and the whole thing is multiplied by a uniform mesh size factor that you may want to enter. If, for example, if you're making like a convergence study, you can ask 0.5 or 0.25 to uniformly reduce the size everywhere. So what we're going to use in the next slide is we're going to specify the mesh size explicitly through functions, through fields. And when that's the case, we want to tell Gsmh to not interpolate the size from the points, because there might sometimes be a conflict between the sizes, or you want to avoid like parasitic small sizes to spread from the boundaries. And so we're just going to turn off those interpolation by setting those 3 options: size from points, from curvature, and do not extend from the boundary, to prevent conflicts between our size field that we assume is correct and the size we might have entered on the points. So a couple of fields that are available in Gsmh, and they're very useful to define quickly a size field, is, for example, the joint use of 2 fields. The one that is called distance, which it's pretty self-explanatory. For example, it's a field that computes the distance to a point, to a curve, or to a surface, and you typically feed it to another field like threshold. So, for example, if you want to create a distance field in the .geo, for example, in foo.geo script, you're just going to create a new field. It starts at 0. It's going to be called distance. You're going to give the list of the points you want to calculate the distance from. For example, I just give this point, P1, and I want to compute the distance from this curve. And this is the number I want to use to discretize the curve. So this is going to compute the distance from those 2 entities and take the minimum, I think. Yeah, the minimum. And then you're going to typically feed it to threshold. Threshold is just essentially a heaviside or a RAM function. It's the minimum value you give for the size if the field given is lower than the distance, than the minimum distance. It's the bigger size if it's bigger than the bigger distance, and then it's an interpolation scheme in between, and you can choose the interpolation scheme. So for example, if you want to create it with the GeoScript, you're going to add a new field. Field 1 is going to be threshold. The input we're going to give is 0 because we want to give the field 0 distance. and then we're going to vary the size between our characteristic length over 30. So from here, I mean, if it's between the point and this radius is going to be 0.15. If it's further than this line from the point, so here it's going to be 1.5, and between the two it's going to interpolate. And when you use this size field to mesh, I mean, it's a lot of words, but this figure probably sums it up very good. This is like this. So it's small from the point, and then it interpolates, and then it's larger. Okay. Another very useful field is the math-eval, which essentially evaluates the mathematical expression you give in a string of characters, and you can use F0, F1, etc. to refer to the previously defined fields. You can use the XYZ coordinates, and you can use a list of built-in functions such as absolute value, cosine, etc., etc. So, for example, I create a new field, a new math-eval, and the F attribute is going to be this string of characters. So it's going to be a minimum size is going to be 0.05, and then I'm going to add a cosine in the domain. And you can also give as an input for example, the distance field, which is defined. So I didn't show this one, but you can give F0 to reference to the distance field and use it as a function. And another very, very useful field is, of course, the minimum, because usually you want to take the most critical size, and you just give a list of the fields you want to take the min of. So if I want to take the min of my threshold and my math-eval, this is what it's going to look like. Okay, so yeah, and one before we continue, this is a little bit of advertising for the size field I implemented. It's a field that it's an automatically computed size field from the curvature and the closeness of the boundary. So it essentially calculates the skeleton of the geometry, and it's going to divide the space computed through the skeleton by a custom number, which I call endpoints per gap. So you can see two closed objects are going to have the size that is adapted here in the gap. Okay, it's a bit right now it's a bit less handy because you have to first give a uniform mesh on which I compute the skeleton, and then from this data I'm going to give you the field. But it's not just create a geometry and add the field. You have to make the intermediary step of creating a uniform mesh. So we're gonna try to get rid of this. But in the meantime, you can give a uniform mesh and then compute the size field and then remesh to have the adapted size field. Okay, so so in summary, if for example, if we want to use the min between the threshold and the math-eval fields I created, I use the two lines I showed you. We're going to make sure that we do not consider parasitic information from the boundary. So we set all those three values to 0, and we have to make we have to add the very important line. Background field is going to be the number of the field, because if we do not add this, it's not going to consider the field we gave. So we have to specify which of the fields is going to be the background field, and then you can close the script and use Gsmh to mesh it in a way I'm just going to show you on the next slide. So you can, yeah, as I was saying, you can define those fields from the GUI through the mesh set size field options, but I find this to be a bit tedious. So I would personally advise you to do it from the script, but it's whatever floats your boat. And there are a couple more useful fields, for example, a box, which is a window in which you want to define a size, the nice boundary layer field, which helps you compute boundary layers in CFD, and the post view field that I will talk about at the end of the presentation. They're all in the documentation, of course. So now we're going to generate the mesh in command line. So it's very easy. In command line, you use this command. So it's gsmh foo.geo. If you just do this, you open the model like before. If you add -1 or -2 or -3, you're going to generate the mesh in 1D, 2D, or 3D. And it's not going to open the GUI. So if you run gmesh foo.go, it's going to open the GUI, but if you add the flag, it's going to mesh and then close silently. If you want to mesh in the user interface, you can simply open the script we just wrote and then press 1, 2, 3 on the keyboard. Because when we were playing with the GUI before, at the end of the day, Gmesh also created a .go file. So he produced by default an untitled.go file that's somewhere in the current directory when you open Gmesh. You can give some options, of course. You can specify the name of the output file. You can change the format. So there's a buttload of format you can use. For example, this is the Abacus format. This is the INRIA format. This is the native Gmesh format is MSH, and there are different versions: MSH2, MSH4, etc., etc. You can choose. You can handpick your meshing algorithm if you want Delaunay, frontal, etc., etc. HST is the super fast 3D Delaunay Jean-François was talking about in his presentation. You can pick the order of the elements. You can add, this is the size factor I was telling you about before. You can choose the value with which you want to multiply the whole size field. You can specify the min and the min and the max. CL is for characteristic length, so the min and max mesh size. You can specify a file to use as a background mesh that avoids to go through the script to define the background mesh. And this is more advertisement for my size field. You can now call with minus size field, and then you enter the nodes you want to discretize the curvature, the nodes you want to discretize the gaps, and the gradation. That means the factor you want between two adjacent edge lengths. For example, this is a quite finely graded mesh, which means when you how do you call that? The ratio of two adjacent triangles is not that big. You don't allow triangles to grow very fast as you go away from the boundary. That's what I mean. It's called gradation. So a couple of calls, checking the time. Okay. Couple of calls. You can, for example, call gmesh foo.go -2 to mesh it in 2D and save it in a file called mesh in the native 4th edition of the Gmesh format. You can mesh not the same geometry file, another one with the 3D geometry. You can mesh it in 3D with the P2 tetrahedra. You can choose the very fast HST algorithm, and you can save it in mesh.mesh. And for example, you can mesh our geofile in 2D, multiply the whole size by 0.1 and set a minimum size to 0.001, sorry. And some more advertisement for my size field. The example I was telling you about, you can just generate a uniform mesh by calling -2 and set a small factor to the whole thing. You save it in foo uniform, for example, and then you call the size field function on the foo uniform. For example, this means I want 4. Oh, I inverted the two arguments. The first is the nodes per gap, and the second is the nodes per curvature. So I want 4 elements between within 2 closed boundaries. I want 20 nodes on a 2π discretization, and I want it to be quite finely graded. So I want 1.1 as the ratio between 2 adjacent edge lengths. And then this will generate a size field in the P4S format, because this uses the P4S library, which is essentially an octree library, because there's an octree behind to make the size request. And you can now launch again your foo.go script, mesh it in 2D, and use as a background mesh, so this function, the file that was generated by this call. Okay, so it's fairly easy, and you can save it as mesh.msh. It works in 2D and 3D, and it's currently isotropic. I have the anisotropic I have to upload, that you can you can reach me if you feel like using it. I'll be happy to assist you. Okay, so this was for the GeoScript, so the command line using the GeoScript. Now we're going to have a quick look at the API quickly, because I don't think I have much time. So a few words about the API. So API is the application programming interface. It's basically the menu of all the Gsmh functions you can use to program with Gsmh. So that's how you're going to integrate Gsmh in your own program. And you can do it if you program in C, C++, Python, and Julia. So the global structure, essentially the namespaces, you have the Gsmh model namespace, in which you can find essentially the geometry function and the meshing function. So the geometry function includes the built-in kernel, so the geo namespace, and the OCC for the Open Cascade kernel namespace. For example, if you want to add a point in the built-in kernel in C, you're going to use the camel case function Gsmh model geo add point. And if you want to use it in C++, you're going to do it using the namespace syntax. If you wanted to add the point in the Open Cascade kernel, so in the Open Cascade representation, which we're going to do in our example because we're using the circle function, we're going to use Gsmh model OCC add point. And the other main sub namespace is the mesh, which contains the mesh related function and the size field related function. So for example, if you want to generate the mesh in our code in Python, we're going to use gsmh.model.mesh.generate and specify the dimension. And if we want to add a mateval field in a C++ script, we're going to use gsmh model mesh field, the sub namespace for the field function, and then add with the specific syntax, so the name and the tag of the field. And then at the primary level, you also have the Gsmh view namespace, which is going to be used to create visualization and post-treatment instances, which are called views in Gsmh. So you can have the full list and the full signatures of the function in the, for example, gsmh.h or gsmh.py when you download Gsmh or you download the development kit. And they're all explained in those functions and in the doc. And what I'd like to put the emphasis on is that you have a lot more possibilities using the API than with the GeoScript. So it's like it's a bit like playing in, I don't know, in God mode in a video game. You can have access to basically everything you can think of, and it's you have almost full control on the geometries, on the meshing. Whereas if you remember in the GeoScript, there were some points that were created implicitly. Now you're going to control all this. Well, yeah, you can have access maybe more easily. So example with the C++ API. So we want to do exactly the same example a third time, but with a C++ script. We're going to include gsmh.h, the header where all the functions are defined. And we're going to start by initializing the Gsmh functions. You'll always start by initializing, you always need to do it once. We're going to add a model with a name. So it's going to be my beautiful model. And we're going to define a couple of variables. So still the length, I mean the characteristic mesh size, the center of my cylinder and the radius. And we're going to add the points. So if you remember, it's in the namespace Open Cascade. So it's model OCC and the function is add point. And instead of doing point one equal blah, blah, blah in the GeoScript, we're going to add the tag we want at the end. So it's the coordinates, the size, and then the tag I want to give. And an alternate version of doing this is we can create an integer that's a return value of this add point, add line, etc. function. So instead of doing this, I can do int p1 equal gsmh blah blah blah, and I do not call it with the one. So the same idea with the curves. So a new tag is returned if there was none specified. So I'm going to create lines between 1, 2, 2, 3, 3, 4, 4, 1, it's oriented. I'm going to add the circle, and I'm going to create the curve loop. So the curve loop is going to be a function that takes as an argument a vector of the tag, a vector of the tag of my lines, and then the other curve loop is a vector of one element. That's the C1 here, the name, the tag of my circle. And in the same fashion, I'm going to call the plane surface and create it with boundary circle and give it the tag 1. I could also do int surface or surface tag equal Gsmh blah 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 without the 1 here. Once this is done, you have your geometry that exists, but it lives only in the OCC namespace. So if you want to spread the information, spread the good news to all the library, we have to use synchronize. Okay, so synchronize, you do this once you've created your geometry. It requires quite a bit of computation in the background, so don't do it on each line. You do it at the end of your geometry, and it just allows you to access the geometry on, for example, the model namespace or the field namespace. Okay, then we add the physical entities. So in the same fashion, I can either say integer entrée égale the physical group of dimension 1. You have to specify the dimension and the line 4. Bord is going to be dimension 1 and the line 1 and 3. Or if I want to specify the tag, I can do it without calling it with the return value, and I can just add 3 and 4 here. Same for the surface, and then I can set the names. So I don't think you can directly call it with a string of character here, but you can give it a number, and then you can use it in set physical name to name the physical entity. Once this is done, we can go on and, as before, define a few fields. So for example, we're going to add a distance field with a tag. So the main difference is that in the C++ API, the tag starts at 1 and not 0. We're going to give, in the same fashion, we're going to use the function set numbers or set number to give a value or a list of value to the attributes of the field. We create a threshold. We give as an input the distance field, and yeah, the rest is pretty straightforward. It's just the adaptation of our distance, threshold, mateval fields. Right now you also have the set string function, and the minimum, which is number 4, and which is going to be the minimum of fields 2 and 3. So fields 2 and 3 is this one, the threshold, and this one, the mateval. So same as before. The new thing that you can do in the API, if you remember, is you can specify a custom-made size field, so a custom-made size callback. So for example, outside of my main function, I could define my function mySizeField. It takes as an argument the dimension and the tag of the entity, but we won't use it. We're just going to be simple, and it's going to be 0.02 if x is between 1.5 and 1.8. Otherwise, it's going to be 2. Okay, so there's going to be a band of very small elements between 1.5 and 1.8, and then we're going to give this this reference to the function as a set size callback. You can also specify this directly in the main function if you use, for example, a lambda function, but you can just define this outside and give it and give the function name. So don't forget to turn these 3 interrupters off, because we don't want the boundary size to propagate in the domain. And then we simply call mesh generate in 2D. We can write the model, simply gmesh write, my beautiful mesh.msh, and we finalize to free the memory, and we return. And this gives something like this. So it's the same as before, but I added a band of very small elements between 1.5 and 1.8. Okay. It's already 4. I'm going to skip this. This is the exact same ID, but with the Python API. So you can take a look at it if you're interested. Create the geometry, the fields, mesh. It calls the FLTK run, so it calls the GUI at the end, but that's the only difference. A quick word on the visualization. So you can use Gmesh as a somewhat basic, but you can do already quite a bit of fun stuff with it. Application to visualize your results. You can visualize scalar, vector, tensor data. You can either do it in what is called a list-based .pos file. So you essentially, it looks like this. So a view with the name of your view. And you can just add as many entries as you want with the syntax that's given in the doc. So essentially, this is a scalar triangle, and you give the coordinates of its three corners, of its three vertices, and you done the values at each of the vertices. So it's 1 here in black, 2 in red, and 3 in yellow. And then you can add 2 arrows that are vector points. You give the point where it's at, you give the vector value, and that's it. So you can very easily visualize scalar values interpolated on the triangle, or vectors at wherever you want. The other, so it's a handy tool if you have not a lot of data to visualize. If you have a lot and you can associate it to a mesh, it's recommended that you just use the model base. That is, you add, you export your mesh, you do your computation, and then you add a node data entry in your mesh, and you just give the data at each vertices or element of your mesh, and it looks like this. Yeah, so that's just what I wanted to say on this topic. I'm going to conclude real quick with a small example of mesh adaptation. So essentially, we're going to build a size field through the API, through the C++ API, and we're going to use the field post view to use, we're going to use the size field. The size field is really in the form of a post-processing view, which is the item Gsmh uses to visualize. And my whole point is you can use a view to visualize as a background mesh. For example, you can use this result as a background mesh if you wanted to. So for the context, we're going to build a size field from the U velocity in our flow simulation. And the aim is going to have a equivalent representation of the interpolation error between the function and its second order interpolation, because we're going to be using the set P2, P1 Taylor-Hood elements. So we use P2, P1 finite elements to compute the solution. So the velocity field is represented by second order finite element. And if we want to find a bound on the error, we can bound the difference between the function u and its second order interpolation, which we computed on the mesh. So it's given essentially by the third order derivatives and third power of the mesh size. The mesh size is our unknown, and we end up with this expression. So essentially, we're going to have to compute the third order derivatives here. The E here is our target. So we want this error to be the same everywhere on the mesh. And so this is given, this is computed from the derivatives. And then we have this field in the domain. And then we can create a view like this with the scatter triangle and give at each vertex the value of this h. It would look like this. This would create a view 0 in Gsmh, which is my size field, the size of the elements I want to have. And then I can call the post view field to give this as a background mesh. So I'm gonna skip on the code here because it's already 4 p.m. But you can feel free to have a look at it. The size field here is hidden in compute size field because you need I needed the finite element software to compute the size. So essentially, we create the view, we save the view, and we use the view as a field here. Create a post view field. We create the field post view, and we're going to set the number of the view to be used as a background mesh as the view we created with the mesh size. Okay, so I know it's a bit fast, but if you're interested, you can have a look at it and we can discuss. I'd be happy to jazz about it with you. This is how you do it in the .geo script. It's a bit easier, but it's for it's when you have already exported the visualization file. So we're going to merge essentially together the size field in visualization file and the geometry, and we're going to this is going to create a view, and then we're simply going to define the background mesh as the view created by this, and it's fairly easy. So it would look something like this. And you can see in black, these are the smaller sizes. In red, the bigger mesh sizes. Well, actually in white, but it's a little error probably. And it will look like this. So yeah, I think that's mostly the end of my presentation. I'm sorry, I didn't have much time, so I focused on the 2D part. There are many more features you can have access to in Gmsh. For example, all the 3D stuff I didn't discuss. You can of course not waste your time creating your own geometry and simply import geometries from other modelers. You can now reparameterize and remesh. You can essentially remesh STL files, which is very useful. You can generate quad meshes, which are non-structured or transfinite. You can create anisotropic meshes, and I would advise you to take a look at the tutorials on the website, because they're very well done, and you can adapt them to suit your needs. I think that's about it. So thank you for your attention.